Hello friends, welcome to my lecture on Cauchy-Riemann equation. Suppose we have a complex function fz which is equals to ux plus ivy, which is differentiable point x plus iy. This theorem said that let f of fz equals to ux plus ivy be differentiable at a point x plus iy, then z the first order partial derivative of u and v and they exist and satisfy the Cauchy-Riemann equation, which ux equals to vy and uy equals to minus vx. And we can say that del u by del x equals to del v by del y and del u by del y equals to minus del v by del x. They are known as Cauchy-Riemann equation. Let us see the proof this theorem. F prime z equals to limit del z tends to 0, which f of z plus del z minus f of z by del z, and f of z equals to limit del z by del z tends to 0, which u x plus del x and y plus del y plus I v x plus del y and y plus del y minus u xy minus I v xy by del x plus I del y. Now let del z tends to 0 along path 1. So we can say that whenever the function fz is differentiable at point z, then CR equations are bounded to be true. That means they are necessary the function to be differentiable at the point z. So we can let us prove the theorem. Since the function fz differentiable at point, then f prime z equals to del z tends to 0, f of z plus del z minus f of z by del z, which z equals to x plus iy and del z equals to del x plus I del y. Then z plus del z equals to x plus del x plus I y plus del y. Now let us take suppose p and q, here p and q moving parallel to the y axis. After this del y becomes 0 when moves towards p and del x goes to 0 when p to q move along the path 1. Then we assume that the function is differentiable at the point along whatever the point path become moved to the z, that point p limit have to be same. So limit del z tends to 0, x plus del x y plus del y plus I v x plus del y y plus del y minus u xy minus v xy by del x plus I del y. Now let del z tends to 0 along path 1, then after del y equals to 0 and del z equals to del x. So prime f prime z equals to u x plus del x y minus u xy by del x plus I limit x tends to 0, v x plus del x and y minus vxy by del x. Since f prime z exists, we have f prime z equals to ux plus iy. And u plus, then we have to show that ux plus I vx, that is the value of f prime z along path 1. This most equals to minus I uy plus vy, which uy equals to minus vx. Now let's see path 2. Del z tends to 0 along path 2. Then after del x equals to 0, we have del z equals to I del y. And here f prime z equals to limit del y tends to 0, u x y del y minus u y plus limit v x plus y plus del y minus v x y by del y, which f prime z equals to minus I u y plus v y. And 1 and 2 we satisfy u x equals to v y and u y equals to v x. Thus Cauchy-Riemann equation must hold z if f is to differentiable at point z. If these equations are not satisfied at point z, then fz cannot be differentiable at z. Along path 2, here p and q, when del z goes to 0 along path 2, so we have ux equals to I vx, that is value of f prime z, right? Then the function, the f is to be differentiable at point z and these equations are not satisfied at the point z, then fz cannot be differentiable. Let us take an example. Examine the nature of the function fz equals to x square y5 x plus iy x for y10, which z not equals to 0 and f0 equals to 0. In a region including the origin, fz equals to u plus iy iv and u equals to x square y5 by x for y10 and v equals to x square y6 by x for plus y10. Check its CR equation, partial differentiable. Examine the nature of the function. Nature of the function means we check CR equation, partial differentiable or not, and which is analytic or not. First we have to check CR equation. So we know that ux equals to vy and uy equals to minus v of x. So del u by del x ux comma 0 minus u 0 0 by x, which is equals to 0 0 0 minus 0 by x, which is 0, and del y by del x also 0, del v by del x also 0, and del v by del y 0, which ux equals to vy and uy equals to minus v of x. CR equation satisfied. Then we know that every constant function is continuous. Now we check the function is differentiable or not. So f dash 0 equals to limit z tends to 0 fz minus f0 by z, which is equals to x square y5 x plus iy, and f0 given, f0 equals to 0 given, and we assume using path x4 plus y10 equals to 0, and this path y5 equals to mx square. So we assume this equals to m by 1 plus m square, which depends on m. M is slope, so limit not unique, so not differentiable, and f is not analytic.